mechanics of materials, fixed and released method. In this example, we want to focus our attention on a very fast approach to solve our problems, and it's very useful in multiple choice questions. So if we have a system consists of cantilever beam handling distributed load of W attached to a spring with the stiffness of 3EI over 2L cube. We want to know what is the force inside the spring as well as the formation of point B. So if you remember, we have solved this problem with the consistency of the formation, solution 1, which I will upload the link for this solution 1 in the description of this video if you want to review that one. And this one we want to solve it with far simpler and faster approach, which is the fix and release method. So in the solution 2, which is the topic of today's talk, is fix and release method, which is our solution to our fast approach. So in a fix and release method, we have two stages. In stage 1, we will fix the location which we want to calculate the deformation there. So we want to know what is the delta at B. So we locate a roller support at B to have that part fixed. That's why we call it stage 1 fixing, and remove the spring. So as soon as we have the system like having the fixed support and removing the spring, now we can easily know what are the supports at A and B. I have also a video which I have calculated the reactions at A and B for such 1 degree indeterminate beam. I will also upload the link to that video as well in the description of this video if you want to review that one as well. And for such a beam, we have like a 5/8 of WL goes to the reaction A, and the other part, which is a 3/8 of WL, goes to RB. So the bigger chunk of energy or force goes by reaction at A, and the smaller portion handles with the reaction at B. As soon as we have the reaction at B, the stage 2 is the releasing stage. So in this stage, we will remove the support from the system. We'll remove the support, the roller from the system, while we keep the reaction of 3/8 WL. RB remains there. So as soon as we have that, now we can easily see the beam and the spring are in parallel. So if we want to calculate a parallel deflection somewhere, so delta at B is equal to F total over K total. F total applies at B. You can ignore the W now because we already distributed W within our system, so there is no need to be worried about. It's just a cantilever beam attached to a spring with a force of 3WL over 8. This system is in parallel and we want to calculate delta at B. So F total over K total in parallel condition. So delta at B is simply the force of RB 3/8 over WL over the stiffness of the beam, which is 3EI over L cubed, plus the stiffness of a spring, which we have both of them. And if you calculate the mass, it's WL to the force over 12EI. So if delta B is this one, Fs is Ks times delta B. We already know what Ks is from the problem statement, and we also know what delta B is. So this is Ks comes from here, and the other part is delta B, which is WL to the force over 12EI. And if you do the math, it just gives you WL over 8 is the force inside the spring. So we get the same result with the consistency of deformation approach, which says the force the delta at B is WL to the force over 12 EI, and the force inside the spring F sub S is WL over 8. Thank you. We'll solve more problems in next videos.